Okay, we're now in section 2.7, proving segment relationships. Number 1 says copy and complete the proof. So we are given that LK and NM are congruent. So let's locate those on our diagram. So LK and NM, those are congruent segments. Also KJ and MJ are congruent. So those are congruent segments. Here's what we want to prove. We want to prove that LJ and NJ are congruent. So we start off by stating our given information. So we're going to take everything here and rewrite it down here. So our reason is just given. We're stating the given information. After that, we have the reason definition of congruent segments. So definition of congruent segments is used when we have congruent segments, then we get to state that their measurements are equal or their lengths are equal, and we can also do that the other way around. If we have that their lengths are equal, we can state that the segments are congruent also by definition of congruent segments. So since I know these segments are congruent, I can say that, for example, LK is equal to NM and KJ is equal to MJ. Okay, so what's the point of that? Well, that's so that I have equations instead of congruent statements. So with equations, I can apply all the properties of algebra to it. So in the next statement, it says LK plus KJ is equal to NM plus MJ. So if I have KJ is equal to MJ, and there it is right there, KJ is equal to MJ. Just like with an equation, when you have an equation, if you add something to one side, you have to add something that is equal to the other side. So since I know LK and NM are equal, I can take this equation and I can add LK to one side and add NM to the other side because they're equal to each other. And then I get this statement. So I took this equation and I added this to this side and this to that side. So that would be the addition property of equality. Equal sign for equality. Then my next reason is segment addition postulate, not to be confused with the addition property. So the addition property is when you add the same thing to both sides. The segment addition postulate is when you have a segment which is made up of two parts. So in this case, we have segment LJ which is made up of two parts, the two parts being LK and KJ. LK and KJ. So if I add LK and KJ together, that gives me the length of the whole thing, LJ. Okay, likewise, we have a segment on the other side, NJ. So instead of trying to squeeze it in there, I'll just put this mark here and then I'll write it up here. So right there, I wanted to say that NJ is equal to NM plus MJ. So once again, that's the segment addition postulate. We stated that this entire length, NJ, is equal to these two lengths, NM and MJ, added together. Then it goes on to say that Lj is equal to Nj, and that's through substitution. Now, for substitution to work here, we have that Lj is equal to Nj in this next step. Now, what did we substitute? We have Lk plus Kj. Lk plus Kj. Well, Lk we know is equal to Nm. So I could put Nm in place of Lk, and Kj we know is equal to Mj. So I could put Mj in place of Kj right here, so that this statement now becomes Nm plus Mj. Nm plus Mj. Now we also know up here that Nj is equal to Nm plus Mj. So if Nj is equal to Nm plus Mj, and through substitution Lj is equal to Nm plus Mj, then we can say that they're equal to each other. Through substitution, we substituted in for Lk and Kj these values here. So substitution, that's how we abbreviate. And then in the final step, it says that Lj is congruent to Nj. So this, once again, is definition of congruent. This is the symbol for congruent segments. And definition of congruent segments, once again, that says that if two segments have the same length, then they are congruent. So since we know that they have the same length in the previous statement, now we get to state that they are in fact congruent by this definition. This is the reason why we get to say it. For number 3, we want to refer to the diagram shown. AP is congruent to CP. So AP is congruent to CP. And DP is congruent to BP. Prove that AP plus DP is equal to CP plus BP. So this length and this length added together is equal to this length plus this length. And I apologize for the diagram here. In some cases, we're using the point R, and in other cases, we're using the point P. So if you see a point P or a point R, those mean the same thing. We could call this point either P or R. So first, here's our plan for the proof. You need to walk through the proof step by step, look over what you're given and what you need to prove. Here you're given two pairs of congruent segments. Use the properties that you've learned about congruent segments and equivalent expressions in algebra to work through the proof. So we state our given information that AR or AP is congruent to CP and that DP is congruent to BP. And we want to prove that this length plus this length is equal to this length plus this length. So we start our proof with some given information. So our given information is stated. Then we want to write something based off of what we know here. So now that we know, since it is stated that these segments are congruent, we can say that their lengths are equal by the definition of congruent segments. So the definition of congruent segments is used if you state that segments are congruent, then you can say that they are equal in length or vice versa through the definition of congruent segments. From here, we're going to use the addition property. So if we take this equation right here, AR is equal to CP. So AR is equal to CP. So we're taking that equation and we're adding DP to both sides. So I'm adding the same thing to both sides of an equation. which the addition property of equality allows me to do. It's like taking an equation x minus 2 equals 5, and to solve it you add 2 to both sides. So you add 2 to both sides of the equation to get a new equation. So after we've done that, then we want to finally arrive at this statement. So let's see, everything in this statement is the same except for this value right here. So is there some way that we can get this to say BP? Well, we know that DP is equal to BP, which means that I can substitute them in place of each other. So if I take this statement and rewrite it, except this time in place of DP, I put BP, then I get what I was trying to prove. And that last step was by the use of substitution. So this would be a good time for you to try two problems on page 147, numbers 2 and 4. Take about 5 minutes or so to look at those. On number 5, it says a tile setter cuts a piece of tile to a desired length. He then uses this tile as a pattern to cut a second tile congruent to the first. He uses the first two tiles to cut a third tile whose length is the sum of the measures of the first two tiles. Prove that the measure of the third tile is twice the measure of the first tile. Here's our plan for the proof. You need to walk through the proof step by step, look over what you are given and what you need to prove. Here you are given two congruent tiles, so A, B, and C, D. And another tile which is equal in length to the sum of the lengths of the other tiles. So EF is equal to AB plus CD. You need to find a way to relate the large tile with the first small tile. So somehow EF and AB. Use the properties that you have learned about congruent segments and equivalent expressions in algebra to walk through the proof. So first we state our given information. So we know that the first two tiles are congruent. So that's A, B, and C, D. We also know that the first two tiles, their lengths added together is equal to the length of the third tile. So AB plus CD is equal to EF. And we want to prove that if we multiply the length of the first tile by 2, then that will be equal to the length of the third tile, EF. So based off of this given information, let's state the given information. That's how we start the proof. State that given information. Then, since we know that these two segments are congruent by the definition of congruent segments, we get to say that they have equal length. So since AB is congruent to CD, then by the definition of congruent segments, the length of AB is equal to the length of CD. From there, we're going to use some substitution into this initial statement. So we're going to rewrite this statement, but we're going to substitute something in for something else. Since we just proved that AB is equal to CD, let's put AB in place of CD into this statement. Now it would say AB plus AB is equal to EF. So that's through the property of substitution. And then we're almost there. If we simplify this, so AB plus AB, or in other words, we can also use substitution. AB plus AB is equal to 2AB. So substitute 2AB in place of AB plus AB. We can also, in this step, we could say simplify sometimes, or combine like terms. So AB plus AB is equal to 2AB, which is equal to EF stays the same in the equation. So based off of our given information now, we've shown that EF is equal to 2 times the length of the first tile, AB. On number 7, we want to prove the reflexive property of congruence, theorem 2-2. So our plan for the proof, you need to walk through the proof step by step, look over what you're given, what you need to prove. Here, you are given a segment. You need to find a way to relate the segment to itself. Use the properties that you have learned about congruent segments and equivalent expressions in algebra to walk through the proof. So the reflexive property of congruence states that a segment will always be congruent to itself. So we are given nothing but a segment, segment AB. So in our proof, we state that we're given segment AB. Then, based off of our reflexive property of equality, that's what it should say here. So the reflexive property of equality states that something will be equal to itself. So the length of AB will be equal to the length of AB, which is different from what we're trying to prove, which is that the segments are congruent. But now we can state that based off of this step by the definition of congruent segments. So we write the definition of congruent segments when we have two lengths being equal and then the segments being congruent, or vice versa. If step 2 said segment AB is congruent to segment AB, then we can say that AB is equal to AB also by the definition of congruent segments. On to number 9, we want to prove the following: that if segment SC is congruent to HR and HR is congruent to AB, we want to prove that SC is congruent to segment AB. So, for our proof here, we're given segments SC is congruent to HR, HR is congruent to AB, and what we want to prove is that SC is congruent to AB. So basically what we're proving here is the transitive property of congruence. So, in our proof, state our given information. Since we have a congruent statement, by the definition of congruent segments, we can say that the segments are equal in length. So that would be the next thing to state here, that SC is equal to HR, since they are congruent, and HR is equal to AB, since they are congruent. From here, we are using the transitive property of equality, which says that if A is equal to B and B is equal to C, then A is equal to C. So in this case, our A is SC, our B is HR, and our C is AB. So if SC and AB are both equal to HR, they have to be equal to each other by the transitive property of equality. And then finally, what we wanted to prove is not that they're equal in length, but they are in fact congruent. So we can state that by the definition of congruent segments as well. So definition of congruent segments works either way, as you can see from step 1 to step 2, congruent to equal, step 3 to step 4, equal to congruent. And it's still the same reason, definition of congruent segments. So this would be a good time for you to try numbers 6 and 10 on page 148. On number 11, if E is the midpoint of DF, so E is directly in the middle of these other 2 points, and CD is congruent to FG, so those two have the same length, then we want to prove that CE is congruent to EG. So you need to walk through the proof step by step, look over what you're given, what you need to prove. Here you're given a congruent segment and a midpoint of a segment. use the properties that you have learned about congruent segments and equivalent expressions in algebra to walk through the proof. So we are given that E is the midpoint of DF and that CD is congruent to FG. So that's what it states up here. And this is what we want to prove. So we are proving that CE is congruent to EG. So let's start by stating our given information, this part right here, and see if we can say anything based off of that information. So we see that if E is the midpoint of DF, then that means that it's going to split it into two congruent segments, which means that DE and EF will be equal in length. So you might be able to see that clear up here. If this is the midpoint of this, then this segment and this segment are congruent, and that's by definition of midpoint. So DE is equal to EF. By definition of congruent segments, since we stated that CD is congruent to segment FG, by definition of congruent segments, we can say that CD is equal to FG. From there, we're going to use the addition property of equality. So if we take statement number 2, DE equals EF, and we can see that right here, DE equals EF in the middle of this equation, then we're going to change the equation by adding the same thing or equivalent things to both sides. So on the left, I added CD. Well, in the previous step, it says that CD is equal to FG, so I can add either CD or FG on the right, since I added CD on the left. So I added CD and FG to this equation, and I get a balanced equation, a new balanced equation here by the addition property of equality. From there, I'm going to state the segment addition postulate for segment CE and EG. So remember, that's what we're trying to prove congruent. So back here, the segment addition postulate says that CE will be equal to these two parts added together. So CE is equal to CD plus DE, and EG is equal to these two parts added together, EF and FG. And that's what we get in step 5. So CE equals CD plus DE, EG equals EF plus FG. Then in the next step, well, we noticed in statement 4 that CD plus DE is equal to EF plus FG, which means that they're interchangeable. So in step number 5, we can take CD plus DE out. We can put EF plus FG in its place, and now I have CE and EG both equaling EF plus FG. Therefore, through substitution, CE is equal to EG. I took this out, I put this in its place, and therefore I can say that these two are equal to the same thing, so they're equal to each other. And if they're equal in length, by the definition of congruent segments, I can say that the segments are congruent. So segment CE is congruent to segment EG by definition of congruent segments.